I'm happy to have Alberto here. So he already was at the panel yesterday and give some nice insight and make you very curious about his talk. And I'm also very curious about this. He's working for Huawei Sweden, and they looked also in identification codes. And his title is a little bit long. It's about identification codes in 5G wireless networks and a view on potential application in future wireless networks. So the stage is yours.
Thank you. The title is already an outline, actually. Good morning. Thank you. Thank you, Christian, for inviting me. This was a very nice workshop. I was very interested in knowing at what point is the research and identification codes, and this was very useful and very interesting. So, I said my talk is mainly about an attempt that we made recently to use identification codes in 5G wireless networks and for a specific application, which is sending wake-up signals to very low power terminals. To my knowledge, is the first attempt that has been made to bring identification codes close to applications, or at least in cellular networks. The presentation is divided mainly in 3 parts. So I will give some background, which is mainly on wireless networks, wireless access networks, and the kind of identification code that we used to build our solution. And then I will go more in detail on the application of the identification codes to this case of wake-up signal in 5G networks. And then I will give some views on the potential applications in future wireless networks. For this last part, I decided to focus on 2 potential applications that I haven't seen in the scientific literature. So there are a number of potential applications we have also mentioned in these days, for example, digital twins and security and so on. I focused on something which is more close to my domain of expertise, which is physical layer, and in particular as close to, how to say, the application that we developed and we brought to standardization. So I will start with the background, and I like to start with the system view. So the system we are referring to is a cellular network where we have a base station and a number of terminals, and this is the basic structure or component of a wireless access network. We have a downlink channel from the base station to the terminals, which is basically a broadcast channel where whatever the base station transmits is received to all terminals, or a number of terminals, or a subset of terminals. And in the uplink, we have a multiple access channel. So the terminals transmit on the channel, and the base station receives a combination of the signals of the terminal. And the usual, I mean, the most widely used services in wireless networks are data transmission services. Almost all the data traffic is transformed into IP protocol packets, and they are sent down the protocol layers to the physical layer. They are encoded and transmitted. So basically, there is exchange of data blocks by point-to-point transmission. Every data block is addressed to one specific terminal in the downlink. The terminal sends data blocks to the base station in the uplink. And the base station takes care of some kind of achieving some kind of orthogonalization, so making the links from base station to terminal independent. The kind of information that is exchanged is mainly 2 types. Control information, which is used to provide indication to terminals, to schedule data transmissions, to assign channel resources to each terminal, for example, and the actual data transmission, which follows typically follows the control information. Then in the 5G networks, as you may know, one of the main innovations compared to previous networks was massive MIMO. In massive MIMO, we have antenna systems that are made of many antenna elements. They have a capability to focus the energy in quite narrow beams in order to maximize the signal-to-noise ratio of the terminal. So all that, the management of the beams and of the indications about the channel of quality of channel requires exchange of control information. And of course, both control and data information flow on both directions, base state downlink and uplink. So here I can see more or less a protocol stack. So it's the way a data packet, IP packet is sent. It goes through a number of different layers down to the physical layer, which is the one that takes care of, for example, error correction coding, modulation. I have detailed it here, error correction coding, modulation. So after error correction coding, you get a code word which is made of information part. Okay, information part and redundancy. The symbols of the code word are mapped to modulations. There are several kinds of modulations, from very simple QPSK to high order modulations. Now even 1024 point QAM is used when the channel quality is very good. And then each modulation symbol is mapped to MIMO layers. Each layer is transmitted typically within one beam to a certain UE, or in parallel, you can have more than one beam that are used to serve one UE. So you can basically multiplex several data streams to a single UE, so you can increase data rate. So the application that we have been looking in particular for use of identification code is this wake-up application, wake-up signal, where there are, of course, the terminals can be of different types. There is the smartphone that we all have. There are, in the new network application, there may be IoT devices, sensors, actuators, low power devices that have limited energy storage capabilities. So they have to be consume very low power. And so this motivates the recent work that has been done to consider very low power terminals that can switch off their operation, and so they go to kind of a sleep state, and they are waken up by a signal on demand by the base station. So for example, here we have a base station that sends a wake-up signal that carries the ID of the ID of a terminal. The terminal is supposed to react to this wake-up signal by waking up by some action. For example, turn on the main receiver and start operating and start transmitting data. The terminal selection is done by broadcasting to all terminals in the downlink a signal that carries the information about the identity. And the problems here are how to encode the identity, how many channel resources we have, because we have to map these signals to the resources, time frequency resources of 5G signal. How we evaluate performance, and how can we be sure that we can meet certain performance criteria like low error rate. And basically the answers to all these questions have been already given in the identification via channel paper. So the number of terminals that can be identified is, as we know, double exponential in the block length n, and there are coding methods that allow to achieve arbitrarily small error probability, provided that there is randomization in the transmission is randomized. So there is a random source. The transmitter and receiver have access to a random source. More in detail, the arbitrarily small error probability, as we are looking at a kind of transmission that is different from data transmission. So we don't have just block error rate, bit error rate as usual. We have two kinds of probability. Type 1 error probability is the probability that RxI decides that its own ID sub I, was not sent, given that the X sent IDI. And the second type of probability, which is also the, let's say, the missed identification. So the transmitter wants to wake up the given receiver, but the given receiver misses identification, is not waking up. Second type probability is the false identification, or also called false alarm, corresponding to a false alarm rate, which is the probability that the RxI decides that the IDI was sent, but TX sent another ID. Okay, so if we make a parallel between the system that we use for conventional transmission, a simplified system, we focus on the error correction code, encoder and decoder. In the conventional system, we have a message, encoder, channel, decoder, and the decoded message. So we are interested in recovering or providing, let's say, an estimate of the transmitted message. In the identification system, we are only interested in verifying whether the transmitted index was the one that the given receiver with identity I prime is interested in receiving, right? And this is reflected in the performance indicators, because in the first case we have bit and block error rate. I'm only mentioning the main performance indicator. Of course, there are more, but I think that we can refer to these to make a parallel. Block and bit error rate and the spectral efficiency. So how many successfully delivered information bits per second per hertz of bandwidth. And in a similar way, the key performance indicators for identification, as I mentioned, are misdetection rate, which is derived from the probability of the first type, false alarm rate, and again, we can define a spectral efficiency in a sense that captures the number of successful identifications for in a given unit of time for a given hertz of bandwidth, right? So about the identification subsystem, we know that the error correction code and the transmission code are of the same type. So they are sets of code words of equal length, a minimum distance between any pair of code words that allows the decoder to correct a certain number of errors, which is up to half the minimum distance, roughly. And so in both cases, it's aimed at providing almost error-free information transmission. The ID encoder and verifiers are different blocks. So the ID encoder produces a tag based on the identity and on the output of a random source. Then, since it is assumed that we have access to a common randomness in transmission and receiver, then one way to achieve that common randomness is to have a random source. In practice, we use pseudo-random number generator in the transmitter, and then transmit the tag, combine or concatenate the tag and the pseudo-random source, and transmit it. On the receiver side, we have a verifier that splits the tag with this tilde, means that it's the received counterpart of the transmitted tag, which is possibly corrupted. In the same way, we have a random output, a pseudo-random output U tilde, which is a possibly corrupted version of the pseudo-random source output, and then you have a recomputation of the tag based on the received pseudo-random source output and the identity. And then there is a comparison of the two tags, and then if the comparison is successful, then the verifier assesses that I is equal I prime. This is one way of achieving, this scheme shows one way of achieving common randomness. There may be other ways. Actually, what we implemented is slightly different because we have the advantage that our terminals are already living in a network with several data transmission capabilities, so we don't need to transmit So the ID encoder can be based on any error correction code. For example, a code word can be obtained based on encoding the identity, and then the tag can be determined by selecting a given symbol from the code word, the U symbol, where U is the random source output, and then you transmit U and CU. Okay, but doing in this way, not all ECCs are good for achieving identification capacity, and here there are requirements that have been clearly stated in this paper. So the ECC size must be exponential in the size of randomness. The tag bit length must be negligible compared to the bit length of the random source output, and the minimum distance must be growing with the block length. So we have been looking at a particular class of codes for implementation of our solution, which is Reed-Solomon codes. So there is a motivation, which these are codes that have the largest possible minimum distance among so that gives advantages in terms of performance. The Reed-Solomon code is a k-dimensional subspace of an n-dimensional vector space over the Galois field GFQ, where Q is the order of the number of elements in the Galois field. And we can write the code and the encoding process in a conventional coding theory form, where we have C, a message M, which is a row vector of capital K query symbols, G, which is a K times N matrix, and we obtain a code word C, which is a size capital N vector of query symbols, and the matrix, generator matrix Z for a Reed-Solomon code is simply obtained in this way. So we take all the non-zero elements of the Galois field, F0 in the first column, F1 in the second, and so on, and then we raise them to all the exponents between 0 and k minus 1. And simply the message in our application is obtained by mapping a binary identity according to this equation. So we simply map the bits we segment the identity in segments of size R, capital R, and map each segment to a symbol, a query symbol in the field, where the size of the segment is the floor of log2k. Alternatively, the RS encoding can be written in a polynomial form, where each element of the code word can be obtained from the message symbols and from a given element of the field in this way. Sum of mk f sub n to the raised to the k. Or we can consider any primitive elements of GFQ, and then FQ, the elements of the field can be obtained as powers of these primitive elements, the non-zero elements of the field can be obtained as power of these primitive elements for q equals 0 to capital Q minus 2, and then we obtain a similar expression. But in terms of properties of the code, I think the properties we are interested in are the same. They are just alternatives of alternative implementation forms. So Reed-Solomon codes, the important property is that Reed-Solomon codes are maximum distance separable codes. So they attain the largest possible minimum distance according to the singleton bound. The mean is, for Reed-Solomon codes, this distance is achieved with equality. The mean is equal to n minus k plus 1. And so if we pick two code words at random, then they coincide in at most k minus 1 coordinates. So it means that this implies that the probability that two IDs collide, so you have two different identities, you generate the tag for two different identities with a given random source output U, then you have a probability of that the two tags, although the two identities are different, the two tags are equal. And that probability is not larger than the k minus 1 over n. So n minus the minimum distance, which is k minus 1 over n. So the largest is the minimum distance, the lowest is the probability of collision, which implies that the false alarm is low. Using a Reed-Solomon code, it is known that using a Reed-Solomon code for generating identification tags is not optimal because it doesn't meet two of the three criteria for being capacity achieving. So it has been proposed in the literature to concatenate two Reed-Solomon codes, an outer Reed-Solomon and an inner Reed-Solomon. This makes the encoding, but the decoding more complicated, especially if you have to do it at a high rate, especially if you have to do it in a low power terminal. So we know that this is the optimal solution, but we didn't further consider this. Also because I would say the block lengths that we have been targeting are quite small. So, capacity achieving schemes are good if you have large block length and you go in the asymptotic regime, but we are, I think, far from the asymptotic regime in this case. So we prefer to stay to take the low complexity paths in this case. More in detail, how this solution has been developed. First of all, some details about the signals that are transmitted in the downlink and in the uplink, but let's refer to the downlink here in the 5G networks. So the signal spans a given bandwidth, which can be few megahertz to up to 100 megahertz or even more if the transmitter works on the millimeter wave band. In the time domain, which is the x-axis of this plot, the transmission is divided into slots, which have duration depending on the settings, on the parameters, from 1 millisecond to a fraction of a millisecond. Each time slot is a rectangle in this representation, this light blue rectangle. Each slot contains 14 OFDM symbols. An OFDM symbol is this thin vertical bar here, which spans the whole down the bandwidth. And in the frequency domain, the signal is organized in subcarriers. Each subcarrier is kind of you can think of some kind of an independently modulated sinusoidal carrier modulated with a complex value. And in the intersection of an OFDM symbol And a subcarrier, this tiny square there, is what we call a resource element. In a resource element, we transmit a modulation symbol. Can be QPSK, 16 QAM, 256 QAM, and so on. So this is what is usually called the resource grid. You can think of that this area formed of many resource elements, and they form a grid in the time frequency domain. In this region, there is in each slot there are some sets of resource elements that are used for control information. These are depicted in yellow. And that is where all the control data in the downlink is transmitted. All the terminals, all the, let's say, baseline terminals like our smartphones are required to decode the control information in all slots and in all the control areas. So this consumes a lot of power, especially if you have small batteries. You have a terminal which is like those small button-like batteries, or even smaller. It's an issue because every millisecond, in each of these control information areas, there may be several code words, and the terminal doesn't actually, there are a number of possible arrangements of resource elements within this area of the control information code words. So there are several tens of possible arrangements, and each terminal has to do for each control information region has to do several decoding attempts. And most of them are failures, actually, because only a few of them there may be control information, and even less because some in those few locations where there is control information, only few of these are for a given terminal. So a terminal makes a lot of effort trying to decode control information. And that contributes a lot to power consumption. So that's why in the past there have been proposals for power saving techniques that are aimed to reduce power consumption by switching off the receiver according to some time pattern. For example, the base station can configure a receiver to detect only one out of control information only on, let's say, 1 out of 10 slots, okay? Or 1 out of 100. So this is what was called DRX, discontinuous reception. Discontinuous reception. But the problem is that if you have a low power terminal and you also want that the power terminal reacts to requests quickly, so you also want low latency, DRX is not a solution, basically. So you need a way to wake up the terminal whenever it is needed. And that is why the standardization community have proposed this structure where we have a receiver which has a main transceiver. The main transceiver is what we all have in our mobile phones, but there is also a very low power wake up receiver which is tuned to a certain subband of the signal, and it waits for receiving a specific wake up. And if it detects this wake up signal with its own ID, then it generates a wake up command for the main transceiver. The main transceiver activates itself, synchronizes, performs data transmission and reception, and goes back to sleep. So what this we thought when this came up in standardization, we thought that this could be a natural application for identification codes, because in each cell the identity of the terminal is it is a 48-bit word It means that in one cell or in one cluster of cells, there can be up to 2 to the 48 terminal, which is quite a big number if you think about. I mean, it's very good, it's very large. Of course, in reality, it's not like that. I mean, there are many less, but the address space is very large. So we thought that we could take the basic design of a stochastic ID code that was, for example, described, for example, in this paper, which is based on a Reed-Solomon code, and map it to the standard. So we have basically, we describe this the encoding by this chain. We have B, which is the identity of the terminal that we want to wake up, which is a vector of length capital B. We map it to a set of k QRA symbols, as I mentioned earlier. Then we encode it to a code word C of M, which is a Reed-Solomon code word. And then based on the output of a random source, U, we select one symbol from the Reed-Solomon code word, and then we concatenate the Reed-Solomon the Reed-Solomon symbol CU and the random output U and transmit it using an error correction code. So we use for encoding, we use the polynomial version of the Reed-Solomon encoder, and actually we found in this paper some kind of generalization of Reed-Solomon encoding, where you have this polynomial expression which is based on this function E of n, and E of n can be simply alpha to the n, as in this case, as we said, if alpha is a primitive element of the Galois field, and then you obtain Reed-Solomon code, but E of n could be n, so the nth element of the Galois field, which includes 0, so you have a slightly longer code word. The resulting code is no longer MDS, should be, if I remember correctly, a class of codes called almost MDS. So it's like close to maximum distance separable, but one less, one below the bound. But in the end, yeah, we use this one. The properties are very similar, and we tried both options, and we obtained similar performance. So this is the block scheme of the solution, of the first solution that we came up with, which is basically, we have a bit-to-symbol conversion, Reed-Solomon encoder. The random generator here is a very simple linear random number generator. We select the youth symbol of the code word, concatenate, and transmit. And in the receiver, we do the verification step. So we have an identity B prime in the receiver, which is mapped to a message M prime, Reed-Solomon encoded. Receive the randomness U tilde and the symbol C sub U tilde, split them, select the U tilde symbol, and so on. And then we check if the ID detects or not. But this was the first attempt. Then we made an improvement, because we realized that we don't need to transmit one thing that maybe has to be considered is that here the transmission, the random generator output U and the code word symbol CU are of the same size. Okay, so U is an index in a code word of length n-1, where n can be up to q minus 1. So basically, U is between 0 and q minus 1 and q minus 2. While CU is a symbol, a QRA symbol. So basically, they have in bits, they have the same size. So if we find a way to avoid transmitting the random source output then we save a lot. We save half of the resources. And this is basically a repetition of what I already said about the collision probability, so I will skip it. So we came up with this scheme, which is similar to the previous scheme, but we have introduced this new element, which is a randomized rate matching, which takes the output of the UE ID encoder, which is a Ritz-Solomon encoder, interleaves it with an interleaver that is based on the random number generator output, and then a symbol selector which just selects a number L of initial symbols from the interleaver output code word. Then we further simplified. We tried several interleavers, and it turned out that they all had even very simple interleavers like a circular shift of the code word, and we didn't get any performance improvement compared to the very simple circular shift. So at the end, this interleaver in the solution that we proposed is a simple circular shift of the code word by U positions. So that is where the random source output is used to determine the shift of the code word here. So this is an operation, of course, that can be done with very low complexity in the receiver. At the receiver side, we have this. And then, okay, last step is that transmission encoder. As a transmission encoder, since this in the receiver, the decoder has to be run several times during reception of the transmission of the wake-up signal, then we try to keep it very simple. So we use the binary BCH encoder with a correction capability, which is somehow dependent on the number L of the symbols that we select. And the seed, these two randomized rate matching blocks are synchronized. It means that the seed, you see that here we have a seed, we call it seed 0, and here we have the same seed. The seed is exchanged before the terminals go to sleep. So there is a previous phase of the transmission where the terminals are awake, and they can receive all the information. And so in that phase, the G0B, the base station, distributes the seeds to the terminals. They might be user-specific seeds, and it's not said, or it could be a same seed for the whole cell, so that they are aligned. And then when the transmission starts, the terminals go to sleep, and transmission of the wake-up signal starts. The wake-up signal is the initial part of the wake-up signal has a synchronization preamble, which is a predefined sequence. At that point, all the terminals start to generate random numbers, and one random number for each wake-up slot. So they are all aligned, and that is let's say, simple but practical way of achieving of implementing common randomness. So this is just a description with a signaling diagram of what I just said. So we have a phase where we have a random number generator seed, which is transmitter to the main transceiver of each of the low power UEs. The main transceiver decrypts the seed and stores it into a memory in the wake-up receiver, and then after that, the UE sends to sleep switch off the main transceiver, and then the transmission of wake-up signals starts. And at each reception of the synchronization preamble, the random number generator is reinitialized. In that way, all of them are synchronized. About performance evaluation, we considered a single antenna transmitter and receiver, although in a base station current base stations do not never have a single antenna, but yeah, I mean, they can use the transmission in this case for beamforming, so for increasing SNR. It doesn't make a big difference from a performance evaluation point of view whether we consider a single antenna base station, and a single antenna receiver is more likely because we have low power terminal, which is most likely a single antenna terminal. Channel models is AWGN, sorry, additive white Gaussian noise, and we considered a fading channel, which is defined in the 3GPP new radio standard, the tapped delay line C, TDLC channel model, which is characterized by this table. There are 24 propagation paths. None of them is a line of sight path. All of them are Rayleigh fading paths. And these are the delays and the relative powers in dB. The delays are normalized and they can be scaled to a certain desired delay spread. In this case, we use quite a large cell, so the delay spread mainly depends on the size of the cell. We use 300, I think, well, it's written somewhere, so 300 nanosecond delay spread, which is quite a large value for a cell. So we evaluated the misdetection probability by, we made simulation, Monte Carlo simulations. So we generated random IDs for a number of IDs in the cell. We encode the ID, transmit it using suitable modulation, add noise and fading, receive it, and then determine, estimate the misdetection probability, which is the probability that the received ID code word C tilde is different than C prime, which is the code word obtained by encoding the receiver ID, given that the transmitted ID is equal to the received ID. And equivalently, I mean, the false alarm probability. So the probability that C tilde is equal to C prime, given that the transmitted identity is not B prime. The results that we obtained are these. By the way, yeah, we also have an analytical derivation that shows that the false alarm probability is approximately Q to the minus L, where L is the number of symbols that we select from the Reed-Solomon code word in the ID encoder. So the length of the tag, basically. So the longer is the tag, the lower is the false alarm probability. This is the average false alarm. It's not the worst case. So it doesn't map to the initial performance evaluation that I've been mentioning in the initial slide. So it's a slightly bit different, but anyway, it's quite intuitive that it's if you have a longer tag, then the false alarm decreases. What was less intuitive to us, at least, is that this quantity is almost independent of SNR. So, and this has been verified by simulation. So this is the simulation we obtained for AWGN channel, where we compare to uncoded transmission. Well, you may wonder if this can be considered a fair comparison or not. We made a comparison, we proposed this solution as follows. Since at that time the standardization community was discussing whether to transmit the identities with some error correction code or not, and it seemed that the dominant view was that it didn't need any error correction code, and the ID is 48-bit long, then we said we can transmit in the same 48 bits, so using the same amount of channel resources, using an ID code, but providing better performance. So that is why we compared with the uncoded transmission. So the misdetection probability of uncoded transmission is this black curve here. And what we obtain with the identification code is depending on whether we select only one, the tag is one Reed-Solomon symbol, two or three, we get three different misdetection probability. Why L equal 3 is worse than L equal 2, L equal 2 is worse than L equal 1. If we have L equal 1, we have a shorter tag, so the error correction code, the transmission code, has a lower rate, and it has a larger error correction capability. So that's why we get better performance. With longer tag, we decrease the false alarm. The red flat lines are the false alarm probability. By increasing the number of symbols in the tag, we decrease the false alarm rate, but in the same time, we have more information bits in the input of the transmission encoder, so the transmission encoder has a higher rate and a lower error correction capability. So that is that explains how the curves are arranged in this way. The error correction code, as I said, is a BCH code of length 48 bits. It's actually a shortened code because BCH has a length which is a power of 2 minus 1, I think. It is shortened to 48 bits, and the input is 7 times L bits. Yeah. The BCH code word is sent to a modulator, which is an on-off keying modulator, and which transmits one OK symbol for each OFDM symbol on 48 subcarriers, so on a bandwidth of 144 megahertz. The RNG is a very simple linear congruential generator, so it computes a seed at time tau plus 1 based on a seed at times tau by multiplying by an integer constant and adding another integer constant. These are the constant, and it's been taken by numerical recipes book. Similar evaluation on the fading channel. On the fading channel, all the gains are like more compressed in smaller SNR ranges, but anyway, we can see that the gain that we obtain in misdetection probability compared to uncoded transmission is still several dBs. I didn't plot the false alarm, but the false alarm is basically the same as in the Gaussian case, so it should be. Yeah, I think that this, a few things about how it went actually, how it's ending in the standard this week. No, next week and in the end of May, there will be the 2 final meetings in the standardization for this topic. Actually, the ID code didn't make it actually to the standardization. But at the end, people realized that it was necessary to include an error correction code, and as it is done usually in the standardization process in this way, they pick one of the codes from the set of codes that are already available in the standard. In the particular case, they agreed to divide the UEs in a cell in subgroups, where there are at most 31 subgroups, plus a group that includes all the UEs in the cell, which has its own ID, and that ID is used to wake up all the UEs in the cell. So in total, we have at most 5 bits of information. Those 5 bits are encoded using the standard error correction code for short block length, which is a binary rebuilder. It is not binary, it's derived from a binary Riedmüller code of second order of length 32 bits. It's kind of a augmented subcode of a second order Riedmüller code, because there have been some, it's not exactly Riedmüller code because there has been some computer search to optimize the generator matrix. And at the end, the Riedmüller code words are truncated in order to adapt to the number of available resources. The code word bits are Manchester encoded. Manchester encoded means mapping 0 to 10 and 1 to 01, for example, so that you have in each symbol, for each bit, you have a transition, either a positive transition or a negative transition. This helps synchronization and helps to detection, especially if you have a very simple detector. So, and then the Manchester encoded code word is mapped to on-off key, is modulated by on-off keying, and then mapped to a subband within an OFDM symbol. So in the band, there is a number of subcarriers that is allocated to the wake-up signal. And this signal structure has been proposed a bit to allow very simple implementation of receivers. So the receiver can be, in principle, can be a very simple receiver like this. So you have the antenna, you have some RF stages, a bandpass filter, which is tuned to the wake-up signal bandwidth, so it discards all the data transmission in the other subcarriers, and then very simple energy detector, which is, in its simple case, a resistor and a capacitor. And then you sample the output of this, and you get the bits, basically. So, yeah. So, well, okay. So I have as I said now, I mean, this attempt to bring ID codes to specification to standard was not successful, but we have been learning from this some important concepts. One is that identification codes are a natural way for efficiently transmitting some control signals like commands to when you have, especially when you have many devices or where you have many control signals to send to a number of devices in a cell. So now the kind of signals that are being sent is in the current networks are many signals are let's say single bit signals like on off, up down, wake up, activate, deactivate, switch on off, or data decoding acknowledgements also. Every time a decoder decodes a data block successfully, it sends back an acknowledgement. If the coding is unsuccessful, it sends back a negative acknowledgement. So there are a lot of these single bit commands that, similar to the wake up signal, are sent in the control part of the 5G network. It was 4G, but for 5G and with 6G, with the expected network and user densification, there is even more. To go more concretely into one of these cases, I would like to mention this enhanced downlink control, potentially the enhanced downlink control channel, where acknowledgements and negative acknowledgements for data decoding that are sent back to the terminals, to the UE after uplink data decoding by the base station could be encoded, for example, by identification codes. So the way that data transmissions are performed is this. You have a transport block, which is the unit of information that is obtained at the upper interface of the physical layer. The transport block is encoded by a low-density paricheck encoder in order to obtain a code word, and the code word is written clockwise to a circular buffer starting from the north point here, this way, okay? So the LDPC encoder always works at a fixed rate. And the transmission, each transmission, data transmission does not transmit the whole code word, but it transmits only part of it. So there is a first transmission, which is indicated here in light blue, that transmits a segment of the code word. Then, when this segment is received, its decoding can be successful or not. If successful, the decoder sends back an ACK signal, a positive ACK. If it wasn't successful, it will send back a NACK signal. And upon receiving a NACK signal, the transmitter will transmit a second segment of the code word, which is RV1, this one. So it will start from here, the purple curve, and then it will transmit if still decoding, the receiver will receive the second segment, combines with the first segment, and then attempts decoding again. If decoding is successful, sends back ACK. If it was unsuccessful, sends back NACK, and so on, up to typically a fourth transmission, and then it will stop, it will give up. But you see that every time there is a data transmission, then there is a production of a control signal, which is either ACK or NACK. This is a signaling diagram where time is the vertical axis. You have the base station on the left and the UE on the right, and this interaction occurs within what is called the HARC process, hybrid automatic repeat request process. So you have transmission of a first segment. If it's unsuccessful, you get a NACK, transmission of a second segment, and so on. So there are lots of these signals flying through between the base station and the UE, and they are single bit signals. So, and then there may be, first of all, there may be several HARC processes going on in parallel for each terminal, because the time that takes to send the packet and receive an ACK would be wasted if there are available resources, channel resources in the middle. So each UE is allowed to start up to, I think it was 8 in LTE, maybe 16 in 5G, parallel HARC processes. So there are even more of this data being exchanged between the transmitter and the receiver. And also, you also have to consider that the target, the adaptation process to the channel quality targets given first transmission block error rate, which is 0.1 for the basic enhanced multimedia broadband service. And for ultra reliability, it is 0.10 to the minus 5. So there will be, in the first case, roughly the ratio of ACK to NACK will be 9 to 1 for EMBB, or 99,999 to 1 for URLC. So it's unbalanced, this kind of message. So the idea here is, I mean, just a proposal, a question, or a proposal for further discussion, whether this could be a possible application for identification coding, where we could optimize transmission of this kind of messages. And even, okay, looking forward to 6G wireless network, we have an expected densification of the network, both on the network side and on the terminal side. Particular robotic IoT is one of the application scenarios where you will have many terminals. There will be a lot of control signaling, which has to be very reliable and low latency. So this makes me think that there are further opportunities to apply identification coding techniques, and hope that there will be benefits compared to conventional transmission. Another application that I would like to mention is integrated sensing and communication, where ISAC, which refers to the capability of a wireless network to simultaneously communicate and sense the surrounding environment. So ISAC will be, well, we are almost sure that it will be part of the 6G standard, because the 3GPP already started to study the channel models in 5G. So they are getting ready, they are warming up for making it become a reality in 6G. And well, there are several, here in this picture, you can see a case where you have two base stations, this one here and this one here. The base station have a dual functionality. One is communication, the other one is sensing. Now, and these two functionalities are integrated in the base station. The way these functionalities are integrated is so far undefined. There are several ways of doing that. One way is just to have two different subsystems, two different radios operating on different bandwidths with different waveforms, and you integrate the information after it has been processed for example, at the application layers. The other way is to use the same bandwidth, the same radios, the same antennas, but some waveform that is designed to provide both communication capabilities and sensing capabilities. And depending on the parameter settings, you can trade off capacity of communication link or accuracy and accuracy of the sensing. There are also several variants related to who sends the sensing signal and who receives it. So there are several possible configurations. The basic one is the monostatic sensing, where you have a single sensing signal emitter, which is also the site that receives back the sensed signals, the reflected signals, like more or less like a radar system, right? And then there are the bistatic and more in general multistatic cases where you have the emitter of the sensing signal and the receiver are not the same system. Okay, so this opens up a number of issues regarding how to coordinate the network nodes in order to be able to process the received signal and obtain some meaningful information. And of course, you also have the variants, the bistatic variants. Also the bistatic versions where on one side you have the network and on the other side you have the terminal. So, and you can use actually the signals, the sensing signals that are transmitted or reference signals, because one option is to also exploit the reference signals that are already transmitted in the communication signals that are used for the purpose of channel estimation, reusing those signals for sense. So you have the corresponding bistatic variants where on one side you have the network and on the other you have the terminal. One of the important issues of these sensing systems is target association. Target associations means that a system that has sensing capabilities senses the environment, creates its own view, its own map of the environment, but it is also important to know which objects that are tracked by the sensing signals are network nodes. Some objects are buildings, I don't know, trees, artifacts. In general, some other objects are network nodes. For example, in a very vehicular network, it would be important to track the vehicular terminal that is connected to the network, being able to know that in that direction you can send energy and communicate or send control signals. So I was wondering whether this target association could benefit by some identification coding approach where you can send some command specific to the network node and activate some procedure that allows the network to detect that in that point there is a network node, there is a terminal, which could be, for example, I would refer to the vehicular case, a vehicle capable of connecting to the network. And yeah, this is, I think we are at the end, basically. Yeah, one thought was about where thinking about the protocol layer structure of wireless network. Well, the physical layer has been so far has always been built around this bit interleaved coded modulation paradigm, where you have error correction encoder, possibly an interleaver in the middle, and then a modulator. But the key point is that in order to adapt to the quality of the channel, you can select independently the code rate and the modulator. That's the main benefit of BICM. Can we in some way plug in ID encoding so as a physical layer can provide a identification service to upper layer? The benefits would be that this service would be available to all upper layers and applications. Well, maybe not. I don't know. How can we do that? Would that be beneficial, or is it beneficial instead to think of an ID encoder in an upper layer? But how that would be combined with the error correction encoder? So these are all open questions that maybe we can discuss. Yeah, that's I think almost it. I had some conclusion, but yeah, we proposed to introduce identification in 5G for control signal, for a wake-up signal, and then, yeah, as we said, I think we have opportunities in future wireless networks to test whether identification code can give benefits and try to provide increased performance. Yeah. Thank you.
Hi, thank you very much for the presentation. It was really nice. So one part I wanted to ask is I'm not aware that much about the wake up signal part. It's quite new to me. But one thing that stuck is that of course you have to dedicate certain hardware resources for wake up signaling. For the terminals to wake up, and you need a dedicated hardware and dedicated processing to it. So that adds a little bit on the power consumption because you are adding separate hardware to it, and then you have to perform processing to it. So where do you think is the trade-off here compared to a state of the art? So where do you think there is a trade-off? Because there is a power consumption with the wake-up signaling as well. If there is an improvement, so where exactly do you think is the improvement?
Well, I mean, the main improvement that is being targeted here is on power consumption. I'm not sure if I get your question, but what we get here is that we turn off the main transceiver, we leave only the low power receiver on. So the power consumption goes from watts to microwatts, to give you an idea of the order of magnitude, because the low power receiver, this component here, yeah, this component here, which is the one that remains on all the time, has a very, very low power consumption. So, okay, maybe your question was also about we dedicate channel resources.
Exactly. We also
Okay.
dedicate channel resources for it, and then we also have to buy spectrum for it. I don't think people
Yeah.
want it to be open-ended spectrum. So people want it to be secure. So you have to buy
Yeah.
spectrum for it. Then you have to again dedicate resource for it.
Yeah, of course. Yeah. I mean, there is a part of the spectrum that is permanently allocated to wake up signal if the operator decides that he provides that service to its customers, then there will be part of the spectrum, so a number of subcarriers in the spectrum that will be permanently allocated to that. And it's not flexible because once you have terminals deployed, you cannot make them change frequency. So, I mean, it's there, and it will take resources from data transmission, of course. But then, I mean, it's a service that if there are customers that require that services, and so in current situation is that there is no other way with 5G networks to provide that kind of service. So yeah, it's a trade-off actually, yes. And yeah, one thing I can say is that the current bandwidth that is being used is quite large. It's like a 10, 11 resource block, so it's quite large. So and the reason is that you need a larger bandwidth to send more power to the receiver. Since these are very basic, very simple receivers, you have to send more power. So otherwise they will not sense the wake-up signal. So I would expect that in the future there will be optimizations aimed at reducing this bandwidth. So give back resources to data transmission and try to compress the wake-up signal bandwidth to more.
And just one another question. You also propose using random number generators for identification coding?
Yeah, it's a practical way that we found. Yeah, this.
Exactly. So, what do you think the standardization for the random number generator is going to be? Because for sure, we do not want leakage of the seed information, because that would then leak the type of random number generator that's going to be used. I mean, at least not just with the seed information, but at least if we standardize the type of random number generator that's going to be used, then of course there's vulnerability there. So do you think there is going to be standardization for the random number generator as well? And if yes, then how do you think the standardization is going to be?
So if I understand correctly, your concern is about security, okay?
Exactly.
But yeah, I mean this. If you can standardize the random number generator, but not the seed, right? So the seed you can capture in the standard a procedure that doesn't define the seed, but it implies that the seed is the same for all the network nodes, right? So, and the fact that the random number generator, the seed is transmitted in a previous phase through the data channel, which is encrypted, actually protects the seed and in a sense protects the random number generator output sequence. So it's not, maybe, I don't know, we didn't assess the security of this solution, but we think that transmitting the seed, the random number generator seed through an encrypted channel, at least gives some level of protection, right?
Perfect, thank you.
Yeah, I was not here from the very beginning of the talk, so I'm just wondering, I'm just saying so because you might have already said it. The huge reduction in the power consumption that you are speaking of, from watts to milliwatts or microwatts, is it?
Yeah, I mean, I just giving the order of magnitude. So we have the low power, when you turn off the main transceiver, when you turn off the main transceiver in the user equipment here, which is consuming, I don't know, could be hundreds of milliwatts to watts. Well, it depends also on which part, because we are in these studies we are used to consider only the power consumption of some part of the transceiver, which is like the baseband processing, which could be some hundreds of milliwatts, roughly. the wake-up receiver is much less. The wake-up receiver is a very simple circuit which could consume of the order of microwatts.
So like there is a certain percentage like that you are thinking of? Like what's the percentage of reduction between the state of the art and the proposed? Is it like, for example, 90 something percent or less,
Yeah, I
more?
mean, if the main transceiver is 100%, the wake-up receiver, I think, is less than 1%, definitely less than 1, maybe
But
even
this is
more.
only for the power that's dedicated for the control signaling. So
Yeah,
in terms of total power, I think that it would be significantly less, right? The reduction. Because I mean, if you are thinking in terms of a system, then probably you are thinking in terms of a reduction of the total power.
yeah,
And I suspect that the control signaling and the wake up, I mean, the block here or the process here is a small fraction of the whole total power for sure, right?
yeah,
Compared to the data.
Yeah, I don't have exact number, frankly. So but as I said, it also depends on whether you restrict your view to the physical layer or you look at the whole power consumption of the terminal. Like you also have application and processors and whatever that consume power. So yeah, I mean, maybe I can find more precise numbers if you are interested, and we can.
But the work here is not published, right? It's
No, it is published.
It's published.
Published in Globecom 2024.
So it's not like company confidential or something like that. It's,
No, I'm presenting it, so it's not.
Okay, there was another question. Thank you for the talk, and I think the example with the wake-up signals, they combine several interesting concepts for identification. First, I like that here a resource is offered to the positive identification, so it doesn't pain when there is a false alarm, in contrast to some serious alarm applications. And you had also the separation of random transmission and the identification part. So you transmit the randomized part a package earlier than the information.
Well, yeah, sorry.
Or like partly you had the seed, or
yeah, the seed, not the whole random output, only the seed.
Yes, so maybe there could be some further improvement by conditioning on the case of identification and not identification. I don't know if it's minor, maybe minor things which could be saved. And yeah, I like the pipeline concept because it's also in some processors. There are maybe signal processors. There are maybe many stages where the energy consumption increase and where identification could be beneficial. So it could be maybe further be integrated in hardware in the follow-up computation after the transmission happened, because the transmission also causes some reaction, some computation afterwards. How do you think about such concepts?
Yeah, I'm not sure. But I understand that you are thinking of you're talking about the randomization part or the whole identification coding.
One part is the randomization, and the other thing is to further integrate identification to the computation, like when you have, how is it called, when the computation is done very close to the antenna, to the.
Okay. Yeah, so I'm not sure if I understood, but you're thinking about integrating ID coding at different levels in the. Yeah, I mean, sure, it's there are options. Yeah, I mean, the way we did it is because we were looking at that application and those requirements. But I think you can think of several points in the architecture of a transceiver where this could be executed. Not sure if I answered that.
Okay, there's a further question.
You have the performance over this Gaussian channel, right? Evaluation. Yeah. Yes, here. I have the feeling it's not only about the eddy code, right? It's about the identification and plus transmission code. And
Yes.
here, actually, the transmission code is dominant because for the performance, right?
Yeah, for misdetection, yes.
Yeah. Basically, I have the feeling that the identification code is like you just choose the one maybe most convenient one, but the role really to gain a better performance, seems the transmission code is more important for the overall performance.
Well, for misdetection, yes. I mean, if for false alarm, on the other hand, it is perhaps where the identification code shows its performance, right? So I agree that for misdetection, these are typical block error rate versus SNR curves, right? Where you have a stronger transmission code with a higher error correction capability, then it becomes a bit weaker because the tag is longer, then it becomes further weaker because the tag is longer. So you are increasing the rate of the transmission code, you are reducing the error correction capability, so it gets worse and worse. And that is, as you said, where the characteristics of the transmission code show up. On the other hand, with false alarm, which goes down and down as you increase the tag size, that is the characteristic of the ID code. And you can trade off misdetection performance and false alarm performance.
But you mean actually the choice of because they have to work together. So the choice of the transmission code actually has also influenced the identification code.
Yeah, there is.
And also
there is this. Let me go back to the scheme. So this symbols. Sorry. This symbol selector here selects L symbols from the output of the interleaved Ritz-Solomon code word. So with L equal 1, we are actually doing the same as the baseline scheme that I presented before. You select just one symbol. But then, since we are the performance that we evaluated was at fixed error correction or transmission code length, 48 bits, right? So if you have a longer tag and the code word length of the transmission code is always the same, then it means that you have a longer word in the input of the transmission encoder. The transmission encoder has a higher rate, thus a lower error correction capability. So on one side, you lose performance of the error correction code because it is weaker, but you have a lower false alarm probability because you have a longer tag.
Yeah, so this is when the error correcting capability is better on the transmission side, actually you reduce the false identification probability. So there's a balance kind of,
Yeah, when the error correction capability is better, which is this line, L equal 1. So we are just selecting one symbol of the Ritz-Solomon code word, then we have a high false alarm. If we select two symbols, we lose almost 1 dB.
So you increase one, you decrease another one.
Yeah, it's a trade-off. You trade false alarm for misdetection.
Thank you for this interesting talk. I have several questions and some I may ask later, probably.
Okay. Happy to.
But first,
to answer.
one very quick question. The wake-up receiver is an own hardware device, isn't it?
Is
So,
that?
so to have this efficiency gain, the wake-up receiver must be a separate hardware device from the main transceiver.
Yeah, it's
Yeah.
actually a separated. It is okay within in the same let's say case, I would say,
Yes.
but it's a separate hardware.
It's
Yes.
a separate hardware device, which somehow probably influences the decision on which layer identification has to take place.
Yeah.
And then about this seed, I have the question, is the seed, so if I understand correctly, basically you use a pseudo-random number generator, and so you use the same seed multiple times, or what? To generate, to have
okay.
some
I use the
iterative-
same seed at a given time instant. I use the same seed in the whole network.
Okay,
But
yeah.
then the seed is updated.
Yeah.
In each
Okay.
at each slot, the seed is updated. So and the seed in all the network nodes, the base station and the terminals, the seed is updated in the same way.
And at each time slot where you use one seed,
Yeah.
Are you
sorry.
concerned with like system-wide error performance or only user-wise system performance?
It's an average over users.
Okay, so
Average,
yeah,
system-wide.
makes sense. Yeah,
but average, not worst case, average.
And then the output of the random number generator is probably larger than the seed, isn't it? Like you basically you think in terms.
Well, yeah, okay,
If
yeah.
you map it, so my question basically boils down to if you map it to the theory, like the seed is smaller than what you consider the randomness, or what?
Yeah, I mean the seed is a 32-bit. These are all 32 or 64-bit integers. I don't remember this constant. How do they? I think they are 32-bit unsigned integers. So the seed goes as a 32-bit unsigned integer.
Mm-hmm.
And then the output of the random number generator is this u tau, which is seed modulo u max, where u max is the length of the Reed-Solomon code word, which is much smaller.
Much smaller than the seed,
Than the seed.
Yeah, okay.
Yeah. I mean, the seed
So
is
basically,
yeah.
So basically, if I understand correctly, you don't try to like inflate the randomness, but you just you truncate it kind of so that you only use as much of the seed as you need, basically.
Yeah, exactly.
Okay, yeah.
Exactly.
Okay, then I'm fine, because otherwise I would have asked how do you get guarantees if you have less randomness, basically. But, yeah.
No. It's like
It's really
this
random,
is
yeah.
by the way, this is the notation. I mean, it's unconventional notation. It's a modulo u max, where u max is the field order Q, or the code word length if the code word length is smaller than the field order.
Okay, yeah, thanks.
Yeah, thanks.
A short question, like to communicate the seed with the wake-up receiver, do you use the main transceiver or do you have another hardware? Like, so every time you need to wake up, you need to send a new seed also?
No,
this is
no.
done like, I don't know, advanced in time, like previously in time?
Yeah, there is a previous phase up, here we have time proceeding from up to bottom, from top to bottom, and then we have an initial part where all the receivers are switched on, or some of the receivers, but the base station has to take care that all the receivers are fed with the same seed.
Okay. But question
when the main transceiver is on, and then the main transceiver is switched off, and then
the question is like, if some of the receivers are off, then the seed will never be communicated, and then the wake-up receiver will not have the right seed, right, to properly then.
Well, you have to think that, yeah, I understand that there can be some misalignment of seeds, right? That's okay, but we also tried with, instead of having one seed common, one initialization seed common for all the network having UE specific seeds, that doesn't make a big difference, at least in the performance that we evaluated. So the base station has the ability to keep track of all the seeds, even if you have a subset of the UEs who are initialized with a seed 0, or another subset of UEs which are initialized with seed 1, and so on. Base station always have the capability to keep track of all of them and use the right seed with the UE that he wants to wake up. So it
Okay.
doesn't make, it's not a big issue actually.
So it's not a major overhead, right? Like to communicate the seed or
Well, I mean, it's not, I mean, in some time periods, the main transceiver of these devices must be on. So, I mean, communicating a seed requires 1 millisecond at most, or even less. It's like a very short time. So, yeah, it is overhead actually, but I think it's not so big.
Thanks.
Thank you. Some more comments? So perhaps I have a question. You mentioned this joint communication and sensing, as is Isaac. You saw already that we have a poster also about that there, where we use identification. There is
Yeah.
an idea. What we have is to create the randomness of the noise somehow, or of the sensing, or you can use channel noise, or you can use sensing, and then try to create randomness for this. So you make use of that. For example, if you sense something and it comes to the receiver and it goes back to goes to the sender, then
Yeah.
they both have something in common, and like Pasha did, you can
Yeah.
create some randomness, and then you can use it as a first part for the identification and somehow increase then the rate if you didn't have stored it, but you can create some more randomness somehow.
But
Did you think about
Ye-
such things, or is it enough to store it for you, just send
But-
it beforehand?
But why you need a feedback channel?
Yeah, you need the feedback is in our case the sensing. In our case, we think also about a car which is going in front of you. Perhaps in your picture, we want to wake up his sensors or something like this, and so we get a reaction back, and so he got something, and because of the sensing, we got some feedback, and so we have something in common, and the idea is to use this to create randomness.
Yeah, I think it's an interesting. No, we didn't think. Yeah, it's an interesting way if you can have kind of an handshake with that
Yes.
brings feedback, brings randomness.
Mhm.
Yeah, that could be an interesting evolution. Yeah, answer.
Okay, then
Yeah.
thank you again.
Thanks. Thank you.